तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This course is titled Fundamentals of Operations Research. In this course, you will learn the various tools of operations research such as linear programming, transportation and assignment problems and so on. Before we begin, let us see what operations research is. Operations research is also called OR for short, and it is a scientific approach to decision making which seeks to determine how best to design and operate a system under conditions requiring allocation of scarce resources. Operations research as a field primarily has a set or collection of algorithms which act as tools for problem solving in chosen application areas. OR has extensive applications in engineering, business and public systems, and is also used by manufacturing and service industries to solve their day-to-day problems. The history of the OR as a field goes up to the Second World War. In fact, this field operations research started during the Second World War, when the British military asked scientists to analyze military problems. In fact, Second World War was perhaps the first time when people realized that resources were scarce and had to be used effectively and allocated efficiently. The application of mathematics and scientific methods to military applications was called operations research to begin with, but today it has a different definition. It is also called management science. The general term management science also includes operations research. In fact, these two terms are used interchangeably. A set of tools that are used to solve problems is also called management science. And today OR is defined as a scientific approach to decision making that seeks to determine how best to operate a system under conditions of allocating scarce resources. In fact, the most important thing in operations research is the fact that resources are scarce, and these scarce resources had to be used efficiently. In this course, we will primarily handle these topics. We start with linear programming. We will introduce you to formulations or problems to formulate in linear programming. We will do 4 examples there. We will also spend a lot of time on solving linear programming problems and understand the various issues associated with the solution. We then get into a specific title called duality and sensitivity analysis, where we explore this linear programming topic further. Then we move on to 2 important problems called the transportation problem and the assignment problem, and then we do dynamic programming, and then we also spend some time on deterministic inventory models. So these will be the topics that we will be covering in this course. Linear programming was first conceived by Danzig around 1947, at the end of the Second World War. Very historically, the work of a Russian mathematician was to have taken place in 1939, but since it was published in 1959, Danzig is still credited with starting linear programming. In fact, Danzig did not use the term linear programming. His first paper was titled Programming in Linear Structure. Much later, the term linear programming was coined by Koopmans. The simplex method, which is the most popular and powerful tool to solve linear programming problems, was published by Danzig in 1949. So this is the brief history of this field called linear programming. The first title is called Linear Programming Formulations, where we try to introduce to you how to formulate real life problems as linear programming problems. and to understand the various terminology that is used in formulating linear programming problems. We begin linear programming with an example. So let us consider a small manufacturer making two products called A and B. The two resources are required, which we call as R1 and R2 to make these products. Now each unit of product A requires 1 unit of R1 and 3 units of R2. For example, we have these two products A and B. The two resources are needed, R1 and R2. A requires 1 unit of R1 and 3 units of R2. B requires 1 unit of R1 and 2 units of R2. The manufacturer has 5 units of R1 available and 12 units of R2 available, and the manufacturer also makes a profit of rupees 6 per unit of A sold and rupees 5 per unit of B sold. So this is the problem setting that we are looking at. Now what are the issues that this manufacturer faces? One, the manufacturer would like to produce in such a way that the profit is maximized. How does the manufacturer go around formulating his problem? Now the first thing is the manufacturer has to decide on the number of units of A and B that is to be produced. It is also reasonable to assume that the manufacturer would produce this A and B in such a way to maximize the profit. So the first thing that the manufacturer has to do is to decide or determine how many units of A and how many units of B he or she is going to produce. So we first call these as X and Y. So X be the number of units of A produced, and Y be number of units of B produced. So if the manufacturer produces X units of A and Y units of B, then the money that the person makes or the profit that the person makes, which we call as Z, will now be 6X plus 5Y. Now the manufacturer would ideally like to produce as much of A and as much of B possible, but what happens is the availability of these resources will now try and restrict the amount of A and B, that is X and Y, that the manufacturer can produce. So we look at the resource requirement to produce X of A and Y of B. So since each unit of A requires 1 of R1 and each unit of B requires 1 of R1, so total amount of resource R1 required is X plus Y, and what is available is 5. So this X plus Y should not exceed 5, or this X plus Y is less than or equal to 5. It cannot be more than 5. Similarly, 1 unit of A requires 3 of R2, 1 unit of B requires 2 of R2. So the requirement to produce X units of A and Y units of B is given by 3X plus 5Y, and this has to be 3X plus 2Y, and this has to be less than or equal to 12. This cannot be greater than 12. Also we need to explicitly state that this manufacturer will make X and Y which are greater than or equal to 0, that is the person cannot produce negative quantities of both X and Y. Now you can see this here in this PowerPoint slide. The problem is to try, and also since the person wants to maximize the profit, so the profit function Z is to be maximized. So the person would like to maximize, find out X and Y in such a way that the function 6X plus 5Y is maximized, and then x and y have to satisfy these conditions, x plus y is less than or equal to 5 and 3x plus 2y less than or equal to 12, and explicitly stating that x and y have to be greater than or equal to 0, which is what is shown here. Right. Now this is called formulating a linear programming problem. What we have done now is we have converted the descriptive portion that was shown here earlier into a mathematical form, and this mathematical form is called formulation. Now let us define some amount of terminology, and we try to maintain this terminology consistently in all our formulations. Now the first thing that we define are called what are called decision variables. The two variables that we solve this problem, x and y, are called decision variables, and they represent the output. So whatever comes out as a solution is going to say that we make some amount of a and some amount of b, x amount of a and y amount of b. The values of x and y is the output or the outcome after solving this problem. So the variables that we want to solve are called decision variables, and then we have a function which represents what we are solving this problem for. As far as this problem is concerned, we want to solve this problem to maximize the profit or to get as much profit as we can, and this is the objective that the manufacturer works with. And this function 6x plus 5y, which represents the profit function which is to be maximized, is called the objective function. So the second term that we use is called objective function, which is the purpose of working on this problem. The third set of things are the conditions which actually represent the resources that are available and the resources that have to be used efficiently. So these conditions that we have to satisfy, namely x plus y less than or equal to 5 and 3x plus 2y less than or equal to 12, are called constraints, because they constrain the decision variable from taking as large a value as we would ideally like the variable to take. Because if we simply want to maximize 6x plus 5y without these constraints, then x and y can take as high a value as possible. Now these constraints limit or restrict the decision variables from taking an unlimited or a very high value, so they are important. And then we have to explicitly state in all linear programming problems, we will define what a linear programming problem is formally, we have to explicitly state that these decision variables will have to be greater than or equal to 0. So the four terms that we have tried to introduce here, as you can see from there, are the decision variables, the objective function, constraints, and the non-negativity restriction. So given a problem, when we define all these four and write it in the mathematical form, then that is called formulating a linear programming problem or formulating an operations research problem. We will come to the LP definition a little later. Now as far as this problem is concerned, x and y are the decision variables. The function 6x plus 5y to be maximized is called the objective function. X plus y less than or equal to 5, 3x plus 2y less than or equal to 12 are the constraints, and x comma y greater than or equal to 0 are the non-negativity restriction. So the problem formulation has the four steps: identifying the decision variables, writing the objective function, writing the constraints, and explicitly stating the non-negativity restriction on the variables. Next, in this formulation we realize that the objective function is a linear function of the decision variables, and all the constraints are linear functions of the decision variables. So if you write a formulation such that the objective function is linear and the constraints are linear, then such a formulation is called a linear programming formulation. So an important requirement of a linear programming formulation is the fact that the objective function is linear, the constraints are linear, and we explicitly state that the non-negativity restriction holds. So these are the three important aspects in a linear programming problem. If either the objective function is non-linear, or the constraints are non-linear, or this does not exist, then it is not a linear programming problem. Now we will look at some more examples to understand the linear programming situation. So, this is a simple formulation where we have looked at two variables, two constraints, a maximization objective function. Now, we look at more formulations to understand various other aspects of problem formulation in linear programming problems. Now, let us look at the second example, which is called a production planning problem, and the problem is as follows. Now, you consider a company making a single product, the demand for 4 months are 1000, 800, 1200 and 900 respectively. Now, the company wants to meet the demand for the product in the next 4 months. The company can use two modes of production. We call something as a regular time production and overtime production. Now, the regular time capacity is 800 per month and overtime capacity is 200 per month. To produce one item in regular time, it costs ₹20, and to produce overtime it costs ₹25. The company can also produce more in a particular month, carry the excess to the next month, and such a carrying cost is ₹3. We call inventory cost or carrying cost is ₹3 per unit per month. The important condition is the demand has to be met every month. We cannot have shortages. Now, let us try to formulate a problem that represents this situation and also try to understand a few more things about problem formulation as we proceed. Now, the first thing we do here is we define x1, x2, x3, x4 or in general xj as quantity produced using regular time production in month j, and yj as quantity produced using overtime in month j. Now, these are our decision variables xj and yj, quantities that are produced. Now, let us first write the constraints. In fact, it is important first to define the decision variables, then to write the objective function and the constraints. You can sometimes write the constraints first and then the objective function. You can write the objective function and then the constraints, and then explicitly state the non-negativity. So, in this example we will try to write the constraints first. Now, as far as the first month is concerned, we produce x1 plus y1. We assume that we do not have any initial inventory or any stock to begin with. So, whatever is produced in the first month is x1 plus y1, and we have to meet the first month's demand, which is 1000. So, we write x1 plus y1 is greater than or equal to 1000. We need to produce more than the first month's demand of 1000. In fact, we can do another thing. We can either state x1 plus y1 is greater than or equal to 1000, which implies that x1 plus y1 is exactly 1000 or more than 1000. If x1 plus y1 is more than 1000, then the balance is carried to the next month. So, we can define another term called I1, which is the quantity that is carried to the next month, and say x1 plus y1 plus I1 is equal to 1000. Now, for the second month, we have already carried an I1 here. So, we start with an I1 and then we produce x2 in regular time. Okay, I am sorry. So, x1 plus y1, sorry, x1 plus y1 is 1000 plus I1. So, the balance that is carried, so x1 plus y1 minus 1000 is carried, so that is I1. So, we begin with I1, we produce x2 by regular time in the second month and y2 by overtime in the second month, and that has to be equal to the second month's demand of 800 plus what we carry at the end of the second month into the third month. So, if this left hand side, which is the quantity available at the end of the second month, should be more than the demand, which is 800, and if it exceeds 800, then the balance is carried to the third month. So, here we have this I1 and I2 are the quantities that are carried at the end of the month to the next month. So, Ij is the quantity that is carried at the end of month j to meet the demand of month j plus 1. Similarly, for the third one, we begin with I2 to produce x3 plus y3 will now be equal to 1200, which we have to meet, and then if it exceeds 1200, the balance I3 is carried to the fourth month. Now, for the fourth month, we begin with I3, produce x4 plus y4, and that is equal to 900. We are not using an I4 here because the problem stops at the end of the fourth month, and therefore, we would adjust these quantities in such a way that we are able to get exactly 900, which is required to meet the demand of the fourth month. So, we do not use an I4 here. Plus, we also have a situation that all x y, xj, yj and ij greater than or equal to 0. We have to write the objective function, we have not written the objective function as such. So, what happens? The objective function will be what is the cost of regular time production. So, the cost of regular time production we have is 20. So, 20 into sigma xj, sigma xj represents the total quantities produced in the 4 months using regular time. So, 20 into x1 plus x2 plus x3 plus x4 plus 25 into the overtime production yj. In fact, you could say j equal to 1 to 4 here and j equal to 1 to 4 here, plus whatever quantity that is carried to the next month, we have an additional rupees 3 per unit per month. So, you will have plus 3 into sigma ij, j equal to 1 to 3, and we do not have I4 in this problem. Plus we have xj, yj and ij greater than or equal to 0. Now, what do we want to do? This is the cost function. This being a cost function, we would like to minimize this cost function. So, now this formulation is complete. Now, this formulation finds out xj, which is the quantity produced using regular time in month j, yj quantity produced using overtime in month j. The constraints are given here, and the objective function now tries to minimize the cost function. So, this is the formulation corresponding to the production planning problem. Now, we go back. As far as this problem is concerned, this has actually 11 decision variables. We have left out the I4, and it has, okay, we need to write some more constraints which I have not written right now. The regular time capacity and the overtime capacity are also given here. So, we need to write these constraints. So, these constraints will now be xj is less than or equal to 800 for every j, yj is less than or equal to 200 for every j. So, we have 4 constraints here, we have 4 more constraints here, and we have 4 constraints for the 4 months. So, we have 12 constraints and we have 11 variables, 4 variables x1 to x4, another 4 variables y1 to y4, and another 3 variables I1 to I3. So, this formulation has a minimization objective, which is different from the maximization objective that we saw in the earlier example. It has 12 constraints and it has 11 variables. It also has some equations here. In the earlier formulation, we did not have any equation. we also realize that there are constraints which are of the less than or equal to type here. We have seen constraints of the less than or equal to type in the earlier formulation as well. Right, we have some equations which are here. Now we can do a few more things. The same formulation, we can do a few more things. Now first thing is that we can eliminate these I1, I2 and I3 from this, which can easily be done. For example, we can eliminate this I1 by saying that x1 plus y1 should be greater than or equal to 1000. Whatever is produced in the first month should be more than or equal to the demand in that month, and if there is an excess, that is carried to the second month. So what is the excess? The excess will be x1 plus y1 minus 1000. So this will become x1 plus y1 minus 1000 plus x2 plus y2 should be greater than or equal to 800. So we eliminate this I2 as well. Now this quantity is what is available for the second month. This is the demand for the second month. So if this quantity exceeds 800, then the balance is carried to the third month. So this I2 is nothing but x1 plus y1 plus x2 plus y2 minus 1000 minus 800 will be greater than or equal to 1200, and we eliminate this I3 because I2 is nothing but this left hand side minus 800. So we substitute for I2 here to get this, and we also eliminate this I3. Now we can go back to write. Now what is I3? I3 is nothing but this left hand side minus 1200. So we eliminate this I3 here, and we write this as x1 plus x2 plus x3 plus y1 plus y2 plus y3 minus 1000 minus 800 minus 1200 is equal to 900. So we can eliminate these ij's that are here. Now we have the same number of constraints here, we have fewer variables, we have to rewrite the objective function also here. This objective function now has these ij's, so we have to write this ij very carefully. So this now becomes plus 3 times, as far as the first month is concerned, x1 plus y1 minus 800 plus 3 times x1 plus y1 plus x2 plus y2 minus 1800, and as far as the third month is concerned, x1 plus y1 plus x2 plus y2 plus x3 plus y3 minus 3000. 3000 is the sum of 1800 and 1200. So this is what you carry as I3, which comes in. Right now we have not introduced an I4, and we have an equation here. In fact, we can do something, we can even keep this as greater than or equal to, just to be consistent with the other 3 constraints. And if we choose to do that, then what will happen is we have another term that comes in. You will have a fourth term, which is this x1 plus y1 plus x2 plus y2 plus x3 plus y3 plus x4 plus y4 minus 3900. You will continue to have these 2 constraints, xj less than or equal to 800, yj less than or equal to 200. So you will continue to have these 2 constraints as well. Now the only thing we have done is we have added another term into the objective function. We have replaced this equation by an inequality just to be consistent with these 4. So we now have a second formulation for this problem. We can even have a discussion on this 900. We have a second formulation for this problem, which is the same as what we saw as the first formulation. Only difference is, in this formulation we have fewer variables. We had 12 or 11 variables in the earlier one, we now have 8 variables in this formulation. We had equations in the first one and we now have all inequalities here, and we have also introduced the greater than or equal to inequality to this problem, which we did not see in the earlier formulations also. So, this is a slightly different formulation, but it also represents exactly the same problem that we are trying to model. Now, let us come back to this 900. Now, there are two ways of addressing this 900. One is to put an equation here which will automatically correct the values of x4 and y4 such that we do not have anything excess, and if we put an equation here, then you can leave out this term. If you do not put an equation here and put an inequality here, it means you are allowing for an I4 to exist, and if such an I4 exists, then it is carried into the objective function with the cost of this. Now, both are correct. You can put an equation and leave out this term, you can keep this as an inequality here and then add this, both are correct, simply because any I4 that is carried from here is going to increase your cost. So, the solution will be such that you will not carry an I4, the I4 will automatically be 0. So, in the formulation stage, for the purpose of consistency, you can still keep all these 4 as inequalities, and then you can write this term also. It is just that the objective function has an additional term that comes in this. So, that is kind of shown in this slide. So, you will see that the same formulation is shown in this slide, the requirements for the 4 months, which are the 4 constraints, except that the right hand sides are simplified. You can see that these 2 terms are taken to the right hand side as you see the formulation there, and then you have the same objective function which is shown here, including all the 4 terms, the 3900, and you will also find that all of them are inequalities. So, this is the second way of formulating this problem. Now, compared to the first, now the question is which one is better, which one is superior. Now, there are some very simple guidelines. For the same number of constraints, both these problems have 12 constraints. For the same number of constraints, you can say that a formulation which has fewer variables is superior. So, this is seen to be superior to the earlier one. Both have the same number of constraints, but the number of variables is much less in this. Also, very generally, a formulation that has inequalities is better than formulations that have equations. Most of us are used to solving equations. Later we will see that we convert these inequalities into equations and so on, but as a very general thinking, one may assume that a formulation which has inequalities is better and preferred to formulations that have equations. So, this is better than the earlier one. This formulation we have learnt a few things. We have learnt a minimization objective function. The earlier formulation had a maximization objective function. This formulation we learnt to introduce greater than or equal to type inequalities, which we did not see in the earlier formulation. Now, let us look at a third way to solve the same problem, just to show you that the same problem can have different formulations depending on how you think about the problem. So, let us look at a third way to formulate the same problem again. Now, we introduce a slightly different set of decision variables. Now, we are going to introduce x I j k as the quantity produced in month I to meet the demand of month j using production type Now, we look at 4 months. So, month I can take I equal to 1 to 4, j can also take j equal to 1 to 4, and k has 2 types of production, regular time and overtime. So, k takes values 1 or 2. Now, with this type of definition of decision variable, let us try to write the constraints and the objective function corresponding to this problem. Right. Now, as far as the first month is concerned, first month we produce x 1 1 1 indicates producing in regular time to meet the first month's demand using regular time production, producing in the first month, that is I equal to 1, to meet the first month's demand j equal to 1 using regular time production. So, it is x 1 1 1 plus x produced in the first month to meet the first month's demand using overtime. So, these are the only 2 variables that represent the production to meet the demand of the first month. So, x 1 1 1 plus x 1 1 2, now this should be equal to the first month's demand, which is 1000. Here we are not looking at carrying anything, you will see the way the variables are defined, whatever quantity that is carried is also defined as a decision variable. Now, when we try to meet the second month's demand, the second month's demand can be met in 2 ways, by production in the second month, by production in the first month. In this we also make an assumption that you cannot meet the first month's demand by producing in a later month, to be consistent with the earlier assumptions that we made. Whereas you can produce in a month that is early, carry and then meet the demand of a subsequent month. So, second month's demand can be met by production in first as well as second. So, you will have x 1 2 1 produce in the first month to meet the demand of the second month by regular time, plus produce in the first month to meet the second month's demand by overtime, plus produce in the second month to meet the second month's demand by regular time, produce in the second month to meet the second month's demand by overtime. So, these are the 4 ways by which you can meet the demand of the second month, and these 4 should add to the second month's demand, which is 800. Now, as far as the third month is concerned, we can meet the third month's demand by 6 ways: producing in the first month, regular time and overtime, producing in the second month, regular time and overtime, and producing in the third month, regular time and overtime. So, you end up writing x 1 3 1 produce in the first month to meet the third month's demand with regular time, plus 1 3 2 produce in the first month to meet the third month's demand overtime, produce in the second month to meet the third month's demand regular time, produce in the second month, meet the third month's demand overtime, produce in the third month to meet third month's demand regular time, produce in the third month to meet third month's demand overtime. This should be exactly equal to 1200, which is the third month's demand. Now, we extend it and write it for the fourth month, and that becomes, now this can be done in 8 ways. You can produce in the first month 2 ways, second month 2 ways, third month 2 ways, and fourth month 2 ways. So, you will have x 1 4 1 plus x 1 4 2. This represents producing in the first month to meet the fourth month's demand by 2 types: 2 4 1 plus 2 4 2 plus 3 4 1 plus x 3 4 2 plus x 4 4 1 plus x 4 4 2 is equal to 900. So, we have written the 4 constraints corresponding to the requirement of the 4 months. Now, we need to look at the constraints on the capacities. Now, the first month, what do we do? First month regular time x111 produced in the first month to meet the demand of the first month by regular time, plus x121 I produce in the first month to meet the demand of the second month once again by regular time. So, when we are looking at the first month's regular time production quantity, I will be 1, k will be 1, but j can be 1, 2, 3 and 4. So, you will have 111 plus 121 plus 131 plus 141. Now, these 4 represent the quantity produced in the first month using regular time to meet the demand of 1, 2, 3 and 4 months. So, this should be less than or equal to the regular time capacity of 800. Now, as far as the second month's regular time is concerned, you have x produced in second month to meet the second month's demand by regular time. So, in this case I will be 2 because you are producing in the second month, k will be 1, you are using regular time production, j will be 2, 3 or 4. So, you will have 221 plus 231 plus 241 should be less than or equal to 800. So, as far as the third month is concerned, you will get x 331 plus x 341, because I equal to 3 represents producing in the third month, j can be 3 or 4, you can produce in the third month to meet the third month's requirement or the fourth month's requirement, and k is 1 because they are using regular time. So, this should be less than or equal to 800, and as far as the fourth month is concerned, you will have x 441 to be less than or equal to 800. You have to write 4 more for the overtime production, the only difference being the third subscript will become 2. So, the first month's overtime will now look like this: x 112 plus x 122 plus x 132 plus x 142 is less than or equal to 200, x 222 plus x 232 plus x 242 is less than or equal to 800, x 332 plus x 342 is less than or equal to 800, and x 442 is all 200, because 200 is the capacity that we have. So, this will also be 200. So, you have these capacity constraints written. Now, let us go back and write the objective function. Now, objective function will look like this. I want to minimize the total cost of regular time, overtime and the quantity that is carried. So, in the first month 20 is the cost of regular time production. So, I produce x 111 plus x 121 plus x 131 plus x 141, because I can produce by regular time to meet the demand of all the 4. In the second month, I produce x 221 plus x 231 plus x 241, because in the second month I can produce only to meet the demands of months 2, 3 and 4. So, I have 3 terms. Now, I have x 331 plus x 341, which is the third month's production to meet the demand of either 3 or 4, and x 441. So, this is my regular time production quantities. So, 20 for all this. Now, I have to write a similar term for the overtime production. The only difference is the third subscript k will become 2 instead of 1. So, I will have plus 25 into x 112 plus x 122 plus x 132 plus x 142. These 4 terms represent overtime production to meet the demands of months 1, 2, 3 and 4. K equal to 2 implies overtime. Now, for the second month I will have x 222 plus x 232 plus x 242. Once again, as we saw earlier, in the second month you can produce to meet the demands of months 2, 3 and 4 by over time. You will have two terms for the third month, 332 plus 342, and you will have one term for the fourth month, which is 442. Now, we also need to write the cost term corresponding to the quantities that we are carrying. So, what we do? Plus 3. 3 is the cost that we incur to carry a unit to 1 month. So, all the quantities that are carried from the first month to second month will come here. Produced in second month carried to third month will come here, and produced in third month to carry to the fourth month will come here. For example, we will have x 121. This is carried by 1 month. If j minus I is equal to 1, it means it is produced in a particular month and used in the next month. So, it will incur 3. So, 121 plus 122, these are all carried by 1 month, plus 231 plus 232, produced in the second month to meet the third month, produced in the second month to meet the third month by overtime, and x 341 plus x 342. So, these are the quantities that are carried 1 month. There are quantities that are carried 2 months. For example, x 131 plus x 132 produced in the first month to meet only the third month's demand. So, carried 2 months with a cost of 6. Similarly, you will have 241 plus x 242, and there are quantities which are carried 3 months, because you can produce in the first month and use it in the fourth month. So, you will have another 2 terms that come in, x 141 plus x 142. So, this is the objective function, plus of course all xij, relevant xij k greater than or equal to 0. So, this is the third type of formulating the same problem. You can see that formulation here. You will also observe that this formulation has 20 variables, little more than the previous. Xijk would allow you 4 into 4 into 2, 32, but you have only 20 active variables, the other 12 are not active. 12 constraints, you also have some equations. So, by the same discussion that we had, you realize that this is not a very efficient formulation compared to the second one, because this has more variables, this also has some equations. Nevertheless, this is also a formulation that we can have for the same problem. So, what have we learnt in this second example? Now, we have learnt a few things in the second example, which is called the production planning example. The first thing that we learnt is that there are types of problems which can be formulated as minimization problems. The first example was a maximization problem, second example is a minimization problem. So, objective functions is of 2 types, maximization or minimization. Both had linear objective functions. So, we looked at a second type of objective function, which is minimization in this case. We also looked at the problem where we introduce the greater than or equal to constraints. You do not see them here, but we did introduce greater than or equal to constraints when we eliminated the inventory that is carried. So, constraints can be of 3 types, less than or equal to type that you see here, equations that you see here, and greater than or equal to type. So, we have seen 3 types of constraints in this. Decision variables of course are there. We have also learnt that a formulation is superior if it has fewer constraints, fewer variables. It happened that all the 3 types of formulation had the same number of constraints. So, we could not make out something superior based on fewer constraints, but in general a formulation that has fewer constraints is superior. For the same number of constraints, the formulation that has fewer variables is superior. We also saw that the same problem can be formulated in more than one way, depending on how the person formulating looks at the problem. Now, we did see 3 different types of formulation, and all the 3 formulations will give effectively the same solution if they are correct. Some of them may have more variables, some of them may have less variables. So, 3 formulations that we have seen. We also saw the non-negativity restriction that comes in. So, in summary, in these 2 examples that we have seen how to formulate a linear programming problem, terminology in terms of decision variable, objective function, constraints, non-negativity, different types of objectives, different types of constraints, different types of variables. We will later go through 2 more formulations to understand some more aspects of problem formulation that need to be covered, which have not been covered in these 2.